I'm going to go a little bit quickly because we're not really, oh shit, did I bring any paper? Probably not. Oh yeah, I did. Holy shit. I brought some paper? Did I? No? No. It's too bad for you, Jeff. Oh, there it is. Yes, I did. So before I jump into this, just one last call. Anybody questions about your test? Questions about, yes? Okay. Hold on. I'm not sure what I did with that. That they weren't touchable. Where's your sign diagram? That's the word.
Oh, right.
Yeah. Otherwise, you have no idea if concavity really changes. Yep. Anything else? Anything else? Yes, sir.
Whenever you get a chance, could you go over number 6?
6. Oh yeah. Okay. All right. I need you to understand. Everybody wanted to say what Luigi said. Just say it again. So real quick, I don't know what's happening this semester. I'm really sorry if it's me. I feel like you guys don't feel comfortable speaking up about things, and if it is me, I'm sorry. You can ask whatever the hell, right? It's up to me to go, I don't have time for that. Talk to me later. It's up to me to say that, right? It's not up to you to go, I think this guy doesn't have time, right? So if it is me, I apologize. You know, if it is me, then as much as I say you can ask me anything, you're not going to believe me. It's the way I am. I don't know. Yes. Okay. So that one, everybody really loved that one and wanted more. So, guys, if you don't know what something, well, first off, where on number 6, where does it say it is? Where is it? First quadrant. And I say sketch a graph, right? What is the most basic thing you look for when you're sketching the graph of a function that you don't know what it looks like? What is the most basic thing? So I'll put one that nobody had, but everybody had. Yes? Intercepts. Yeah. I'm in the first quadrant, correct? So what are the two main walls that are containing me? The x-axis, the y-axis. So if I knew where I hit those walls, I just have to put shit in the middle, yes? So what's the x-intercept of that? Everybody had this function, but nobody had this function. What's the x-intercept? What makes that fraction 0? Because the x-intercept happens when the output is 0, correct? 10, good. So for an input of 10, the output is 0. How do I get the y-intercept? Make x 0. What do you get when you make x 0? 5. And then you could, if you wanted to, you could put something in the middle, but it almost doesn't matter how these connect. Make that bigger. Now, can you draw a rectangle that is contained by those walls? Shabo! Yes? There it is. And that's what inscribed means. One person came up and asked me what inscribed was. There were several homework problems that talked about this. Inscribed just means put the thing in there, right? So if I had a circle inscribed in a triangle, you draw a triangle, and then you put a circle in the middle, and then you be careful about what secret society has that as a symbol.
I asked you, and I didn't know if we wanted bottom side or like on the right side.
So I don't know. What's the other option?
There's
There isn't any. Okay, good. Now some of you guys, all right, some of you guys were so close. I almost said funny. We were so close, and I was like, damn. What's the area of this rectangle? I know it looks like a square, but it's a rectangle. Like, how long is this? Does anyone know?
X.
Good. How long is this?
Y.
Kick ass. So what's the area?
X. Y.
Now, what kills me is somebody wrote this, and then they took the derivative of this. I'm like, shit. What are you trying to maximize?
The
Area. What are you going to attack with calculus? What function?
X. Y.
You're maximizing area, so what function are you going to attack with calculus? The function that represents area. Yes, that's the whole idea. If I want to maximize area, I need an area function. I can attack it with calculus. Maximize area means take the derivative of area, get the critical numbers. Yes, yes. You've got the area function there. The problem is it doesn't really represent my rectangle right now. It represents every rectangle. How do I make it represent my rectangle? What do we know? What did this problem tell us? This is what they asked us. What did they tell us? They told me that y is this, and they just I just told you, y is this. So how can you use that in your function? Plug it in. Now some of you guys did that, and then you made the work harder because you did a product. Well, just multiply the x in there, yes? And then you have a straight quotient rule, yes? Once you replace the y with what you knew from the beginning it was, you have a function for the thing they want you to optimize. Then you take its derivative. If I want you to find the minimum amount of fertilizer you need a function that represents the amount of fertilizer, and then I can attack it with calculus, yes? Is that okay? So a lot of you guys kind of danced around this a bit. Some of you guys had some of it written. Some of you guys had both those things written and either didn't know what to do next, or you attacked the wrong thing with calculus. But does that make, you pretty much, I said like 90-something% of the time, you take what they told you and you shove it into what they asked you. And you take that monstrosity you just made and you attack it with calculus, right? And of course, before you do calculus to anything in the universe, you simplify. So that means multiply the x in, right? Gonna get x times that shit, multiply the x on the top. You guys, is that that's shit? That's plenty. That's as much I'm gonna say. Is that all right? Okay. Anything else? Now that I don't know if you open a dam or not, we'll see. Anything else? Anything else you want to hint on and how to start? Yes.
Okay, really quick, how did you get the y-intercept again?
Oh, so guys, remind me. How do you get the x-intercept you make? Y, not in general, any function. Make y 0. How do you get the x-intercept? The y-intercept you make x. Yeah. So I told you the story about I had a function in my last math class. It had like 15 variables in it, and I wanted the w-intercept. I just made all the other variables 0. So I was living in 15-dimensional space, and I was still doing the same thing we're doing now. Just got more variables, let me kill a lot of them, and whatever's left is the intercept for that guy. Yes, sir.
Can we take a look at the 5A?
Oh, okay. So 0 times infinity. If I'm trying to do a limit and it's in the form 0 times infinity, or negative infinity, is that, what's up with that? Do we know the answer to 0 times infinity? That form? No, because it's what kind of form?
Indeterminate.
Indeterminate. That's why we can't determine the answer. Could I use factoring on that? Everybody's got something x natural log of x, yes? For 5, what was it, 5a?
Yes.
You guys all with me? You guys see that problem? It's 0 times negative infinity, which is indeterminate. Back in chapter 2, what did we do? We try to factor, we try to kill it, we try to do something. Here, can we do any of that business? No. Can I multiply by a conjugate? I don't have a route. Can I do any of that shit? No. So what method what's the only other method? The one we learned recently.
L'Hopital.
L'Hopital.
We set it up as a fraction.
Is it currently a ratio? Can you make anything in the universe a ratio? Of course you can. So, like if I have x, The cheesy answer is make it x over 1, but then that's, for example, it's not needed, but I can make x become 1 over x. 1 divided by 1 over x is x. You guys with me? And we did a couple examples like this. So I would take your x, and I would force it down, which means it becomes 1 over x on the bottom.
And then putting the.
And now you have a ratio, don't you? You have natural log shit over 1 over x shit. And that's a ratio. Yeah. Is that okay? Alright. Try to prep you for that. Because I know the guy that makes the test. I knew he was going to do this. Oh yeah, it's me. Y'all didn't pick up that was a joke. Alright, did I miss anybody else? Everybody else got their? Oh, yeah. Anything else from the test? And let me make this suggestion. Some of you guys you sometimes are looking at me like I'm insane, thinking, I have a test tomorrow, and you want me to turn these test corrections in tomorrow, and I can't get them. Do them now. Do them today. Right? I mean, now the reason I give you until the day of the next test is to give you time in case you need time in the middle. Do them soon, before you're buried under the next round of homework, yes? Does that make sense? Do them when you can. Okay. Okay, anything else? Okay, alright. So in general, I do have stuff that I want to get through. But again, I can't stress this enough. Every teacher, it is a big part of their job to balance the questions students have at the moment and the pacing I need to hold to. That's my job, right? Can't stress this enough. It's not your job to go, it feels like this guy's got to get through some shit. I'm not going to ask my question. No, dear God, ask your question. Yes? Okay. With that said, nobody's doing that, so I think we might be tapped out for the moment. Okay. So I want to talk about Newton's method a little bit. This is 4.8, and in case you came in late, extra credit. But I want to talk about it very quickly. I'm going to go through kind of quickly. I do have a handout for it that might help you if you want to try to do this homework. I'll give that out here in a bit. I need more room here. I'm going to accidentally call campus police here to back up. So what Newton's method is, right? This is good old Newton, the guy who did too much shit, should have left some stuff over for other people. Newton's method attempts to find where an x-intercept is, where a function is 0. So for example, if I have a function that looks like this, so there's a x-intercept here. Now, I'm going to develop the process given the graph, but in general, this is assuming you don't really have the graph, or else we just get the x-intercept. I need you to understand, we've already passed this point, but just to be very straightforward with you about this. Students will look at me and say, I got a calculator, it can do this for me. And I will look at them and say, somebody had to program the damn thing. And this is how you program the damn thing to do that. You guys with me? So we are well past the point where you can go, I got this thing. I don't give a shit. You're learning the math that went into getting that thing to do what it's doing. Right? And I hope that some of you guys are a little bit intrigued about that. This little black box, this little magic, hold on. Look at me as I pick it up. Can I touch your stuff? This little black magic box that's just like it does stuff. Okay. So let's say I've got a function, I want to figure out where it equals 0, and I can take a guess. I got a decent little guess I can make. And let's say I guess that the actual 0 is this one. So we'll say this is my first guess. Obviously, I'm wrong, correct? Now, just to remind you, we don't really have the graph, and we're doing this. Otherwise, why would I do it? I can kind of see that I'm wrong. But this is kind of like in the background. I take a guess, and in the background, the graph is laughing at me. You're not even close, human. So here's what Newton's method does that's so freaking cool. And we'll talk about where it's got limitations in a minute. If I find the tangent line, and then find its x-intercept, you guys with me? If I find the tangent line here, and then find its x-intercept, now obviously I am starting off with a decent function, with a decent guess, all this kind of stuff. Would you all agree with me that according to my picture, the tangent line's x-intercept is closer to the x-intercept of the function I'm trying to get? I need you all with me. x1, what was that? What was x1? Where'd that come from? What was x1? It was my guess. And again, I don't have access to the graph, but just to show you behind the scenes, the graph is like behind me. You don't even know it's behind me. And I take a guess and it laughs at me. And let me shut up. I could hear it giggling. And then I make a tangent line, and the x-intercept of the tangent line, is it closer to the actual x-intercept I'm trying to get? Yes. That will happen very often, unless, for example, can somebody tell me immediately where this thing falls apart? If my first guess would have been, yeah, if my first guess would have been here, the tangent line would have just went, holy shit. Do you see what I'm saying? And that's why I reached out to TI, because I wanted to see, because I know they modified their algorithm to account for that possibility. And I just wanted to say, what did you guys do? And that's when they thought I was a competing company, which is hilarious to me. Oh, you missed that story from earlier, right? Yeah, anyway, short story is they thought I was a spy, trying to figure out their approach to things. And I'm like, whatever. I probably would have sold it to HP, but you know, I didn't.
Do you intend to try again?
No. I don't care. What's more important to me is the idea. So, what would I do now? Do I have the right answer? Is my answer correct? No. What would I do now? I'd pretend like that was my first, and I'd just do the whole thing again, wouldn't I? So I would, let me see, Jeff, if I was better in general, I would use different colors, even though I don't think it's gonna show up for you guys. I would take this output, make a tangent line, get its x-intercept. Am I closer now? Am I closer now? Yes. You guys see that? Most of the time, that's what would happen. Unless I'm too far away, right? If I was over here, my tangent line would have taken me back here. Do you guys see it? Let me do that again. If my first guess was here, the tangent line would have taken me back here. Do you guys see that? So either, this only falls apart if I pick a horizontal tangent line position, or my guess is too far away. You guys with me? So when you do the process in the calculator to find a root, do you guys, the zero, do you guys remember how it asks you a left bound and a right bound? Yeah. It does that to make sure it doesn't go too far away. And then it asks you for a guess. Well, obviously that gives it a good initial guess, right? The guess you give it is x1, and then it does this shit. Are you guys at all with me? Okay, maybe I'll do this again.
Sorry, so those processes use the process of elimination.
Not elimination, a process of winnowing, a process of getting closer and closer. And not eliminating anything.
Yeah, it sounds like more like estimation.
It's more like The Price is Right. Higher, lower, higher.
Yeah.
What would I do now? Because am I right yet?
No.
I'm really close. Do you guys agree? I'm really close. But what would I do? I would just do it again. Have you noticed this has happened in class? Have we not gotten something that was supposed to be 7 and it said 6.9999999? Do you guys remember that? We have gotten that. Why? Because it stops when it's within a certain tolerance. It just stops. Because otherwise the process could go forever. So it just kind of goes, let me conserve battery and give them what I think is the best. So when your calculator says 11.9999999993. It's trying to say 12 more than likely. Sometimes it means 11.99, but you guys kind of with me at all?
Yeah.
Now, when I first learned this shit specifically, that opened a whole new world to me. I'm like, I had never really stopped and thought too deeply about what is my calculator doing when I ask it. And to be really honest with you guys, I'm so flippin' old. GI stuff wasn't out yet when I first started, so you know, it came out later. Then you're like, oh my god, what the hell is this thing doing? Alright. I'm not so old that I talked to Newton, alright? Shut up. You still got that Apple Newton? No, I'll throw it away. Damn. Alright, so to put this together, I'm given a function, right? I'm given a function, and I want to figure out where it's 0, and the way we do that is we construct the tangent line at x equal our first guess. You guys with me? So I'm gonna go a little fast. Okay. So I need a slope, so I do f prime of x1, yes? To get my slope. And I need a point, so it'll be x1, f of x1. Yes? So then my tangent line would be y minus f of x1 equals equals f prime of x1 times x minus x1. So everybody cool, that's just y minus y1 equals m times x minus x1, yes? Just forgot to put the more technical derivative. Okay. So then y equals f of x1 plus f prime of x1, x minus x1. Now, here's the trick. So I'm at the stage where I constructed my tangent line. What was the next thing we did? Took a guess, constructed a tangent line. How did I get x2? How did I get x2? What was x2? The x-intercept of the tangent line that I got. And how do I, this came up early, which is beautiful. How do I get the x-intercept of anything? Make the output 0, yes? Are you guys still with me? We've done everything I've talked about so far, we've done. This is just find a stupid tangent line. What is this also called? The linearization. Okay. So if I take that and I set it equal to 0, the answer I get, I will call x2. What answer? How do I get the answer? What am I going to solve for? What's going on? Where am I? What do I solve for, of course? What's the only thing up there that's unknown? X. I know x1, I know f of x1, I know f prime of x1, you know, if I had a function, I could know all that shit. The only thing I don't know is x. What actually makes this thing 0? How do I solve for x? You can do it.
There, f prime's on one side, so.
Subtract f. Subtract f of x1, so that'll be negative. Divide by f prime.
And add x1.
And then add x1. So I get x2 equals x1 minus f of x1 over f prime of x1. Which, you know, some people get a little lost in the sauce. There's no reason in hell you would know the answer would look like that. So, but it's not like a surprise. We just solved the stupid equation set equal to 0, right? I'm not sure what students expect. There's nothing to expect. I don't even know. You set it equals 0 and you see where it takes you. And then you go, oh, that's what it is. Is everybody with me? Y'all can do that, everything I just did. You can do it. Set equal to 0, solve for x. What do you do? And now you just make x2, and then you throw that in, you make x3, and then you throw that in, and you make x4. How do we get x3 now? What would x3 equal? Do I have to do all this shit?
Do the derivative of.
Do I have to do all this shit? No. Do you understand? The whole process would be exactly the same, except instead of x1, I'm now feeding the process x2, yes? So I just keep doing the same thing over and over and over and over and over and over and over until it hits my tolerance. So like if you do this extra credit assignment, the 4-8, if I remember correctly, some of them are like find the answer correct to within 6 decimal points or something. So when you get to the point where 6 decimal points aren't changing, you can stop. That's your answer. That's your tolerance, yes? Okay.
Can you repeat how X became X2?
I call it x2.
Oh,
I call it, so
so what happened to the original X? Because it just doesn't go away.
it's here. I just call it x2. The answer I get to this is an x value, correct? What do we call that x value? Our second guess. So we call it x2. It is x. We just call it x2. Is that cool? I could have called it x2 from the beginning, but I wanted it to exist on its own. It's just what we call the x that we get. Sort of like when we do mean value, we call it c
Yes.
if we want to, right? But it's still frickin' x. It's still the end. Yeah. Okay.
Oh, that makes sense.
Okay. So let me give you this handout. What was on the other side of that, Jeff? I forgot. Oh yeah, that's right. Okay. You guys are gonna peek, but that's okay. And I'll show you one application of this, and then we're gonna get into 4-9. All right. I didn't even bring a calculator. No. Damn it. Did I? Did I not? You never know. Ooh, I did. I brought 2. One of them has battery. It's you. So, here's an example. That's kind of a lame example. This is much more interesting. Do you guys see the problem we're trying to, for number 2, for example? We're trying to solve that equation. But what did I say Newton's method was for? It was finding the x-intercept of a function, correct? And the x-intercept means take a function, set it equal to 0, yes? And that's how I figure out what a function is. I just subtract signs so that I have a function that's equal to 0. That's the function I'm going to feed to Newton's method. That's the function that I want to equal 0. If this function equals 0, is this true? If this function equals 0, is that true?
Yeah.
If this function equals 0, if natural log of x minus sine of x equals 0, add sine of x, do I get this?
Yes.
Yes, there you go. So if I solve this for an x-intercept, I answer this. Do you guys see that? So you can use Newton's method to solve equations. How do I get my first guess? Well, this is where knowing what things look like come in handy. What does a natural log look like? Okay, I'm getting roughly yes. From your perspective, this yes, yes. You with me? Near infinity, grow very slowly. Yes. And that's what it sounds like. Hello. Be a little more specific though. Where does it cross the x-axis? At 1. Good. Natural log of 1 is 0. And then can you give me one more point? Like, do you guys know what E is very roughly? Do you guys know what E is? 2.7 blah blah blah. So let me see. 2, 3. So 2.7, the output would be 1 here. Yes? Natural log of E is 1. Is that cool? Okay. And then sine. What does sine look like? What's the highest sine gets? What's the highest sine gets? 1. Good. And where does it start? At what sign of 0? 0, yes? And then when is it 0 again?
Pi over 2.
Pi, no, pi over 2 is where it loves it. That would be where it's 1.
So
Pi, it's 0, yes? And pi is what? Pi is yummy. No, pi is
3.1.
good with cool with. Pi is 3.1 blah blah blah. Yes? And about pi over 2, which is roughly 1.57, whatever. My scale kind of sucks, but it's okay. So this is what sine looks like. Can you give an estimate? If you draw a sketch of one function and the other, where are they equal? Where they meet?
No.
Can you give a rough guess? 1, 2, 3. 2 point something, yes? So I think for mine, I just guessed 2. You guys with me? But you could guess even better, 2.1 or something. Yes. So, f prime, if f of x is this, f prime is this. You guys with me? How did I get f again? How did I get this? I subtracted sine x over, and I got natural log of x minus sine x equals 0. That's exactly the question that Newton's method would answer, yes? Newton's method answers, where does a function equal 0? That's why Newton's method is perfect for solving equations. If you just subtract a whole side to the other side, you have a function equals 0. Newton wakes up from his grave and says, I can solve that shit. Yeah, all right, man, freaking out. Go hang out with L'Hopital. Okay, so that's the derivative. That's the form we just discussed, yes? I didn't use little n's, but you guys see how this works? x4 would equal x3 shit. x2 would equal x1 shit, yes? So xn plus 1 is equal to xn stuff, yes? I build the next guess off of the guess before. That's what that means. So on top, I put the function evaluated, and on the bottom, I put the derivative evaluated. So just, I'm gonna do this a little bit fast. Are you guys at least with me on the fact of just computationally, just algebraically? You know this shit, yes? You know this, yes? So what goes on top is the function. Isn't that the function? Natural log of stuff minus sine stuff, yes? On the bottom goes the derivative. Isn't that the derivative? Isn't that the derivative? Yes. Is it painful to look at all of this? A little bit, right? Okay. You're all concerned, is it safe to take down? Well, it is. It's totally safe to take down all of this. All right, let me not go there for a second. I don't really know if you're, okay. So here's how you do this, you ready? If you want to try this out for homework, I'm going to show you how to do this. Our guess is, you want to do a better guess than me? What guess do you want to use? 2. Okay, sure. We'll use what I used. So watch this. Hit 2. Enter. Ooh, we've done so much. Now, even better than that, I could have done something else. But hit store in X. We've used that before, haven't we? Store in X. Okay, now watch this. This kicks so much ass. You ready? Can you remind me what that ANS answer, what's it hold in memory? What's it hold?
2.
Currently 2, but doesn't it update every time a new number shows up? That's what it is. You guys with me? That is key. Every time the number on the screen changes, that's what ANS is. It's the last number that was on the screen. So watch this. If I do, what am I supposed to put here? The current guess. What's my current guess? ANS. So if I put answer minus parentheses, yes, I got to tell it what the top and the bottom is. Where'd you go, natural log? Natural log of answer, close parentheses, minus sine of answer, close parentheses, divided by parentheses, 1 divided by answer. So everywhere I see an xn, I'm going to put an answer. minus cosine of answer, parenthesis, parenthesis. Now watch this. If I do this once, that's x2. You with me? That's x2. If I just hit enter, this is the beauty of it. That's like a lot of typing, yes? But now I just keep hitting enter.
Yeah, you can just keep hitting it.
Enter, because now ANS is this, and now ANS is this. And what is this? What is this? What is this? What is it? In our process. That's x2. That's our second guess. What do we do when we have our second guess? We do everything again. And then that's going to be x3. And then I do everything again. And then I do everything again. And then I do everything again. Look how it stopped changing. Do you guys see how it stopped changing? So at least it's good up to here. Yes? Isn't that kind of cool? Sort of. It's nice when there's a lot of front end work, but then at the back end it's like bam, bam, bam. Yes?
Can I ask you why store the 2 on the X then? You just leave it as answer.
Oh, I forgot. That's not what I meant. I'm sorry.
Oh,
I got confused between the two at the beginning. Thank you, Val.
oh, I was just wondering.
The storing of it, I think I just want to remind you that's an option. The ANS is what's important here. You're right. Okay. Did I store it? What did I do? Oh, I stored it in X. I have no idea why. I just want it. Okay. All right. Oh, that's what I was gonna do. I was gonna do it with the storing, but that's stupid. We'll just go straight to the answer. Yeah. Okay. All right. So that's Newton's method. That's section 4.8. One more time. That's extra credit. So I'll build it in WebAssign someday, along with the rest of the next homework, and I'll make it due on the day of the fun. Extra credit. Pretty much always do the day of the fun. So, like I told you earlier, antiderivatives is the next chapter of this class. I'll tell you this, we're going to talk about antiderivatives now, which makes sense, because everything we've done, chapter 3 was chapter 3 was derivative rules, yes? Chapter 4 was, oh, you know derivatives? All right, can you use them? That was chapter 4, yes? End of chapter 4 says, oh, you know derivatives, can you do them backwards? That's where we are right now. You with me? So you don't know an idea unless you can do it forwards and backwards, especially in mathematics. So, number one, just very quickly, well, let me see. That's right, I wanted to do that. Yeah, 1a, that's easy, yes? What's that derivative? Yeah. And part B, how do we do this derivative? What's involved? Good, so how does that work? So the 2 comes down. The power is now 1. Derivative inside. So I can consolidate these, yes? So let me ask you a silly question. What is the antiderivative of 1 over x plus 2? ln of x plus 2. So that's what they literally mean. It's sort of like me saying, okay, 3 plus 5 is 8. What's 8 minus 3? 5. Yeah, so so this is what's going to suck. If anybody out there does not know your derivative rules very well, okay, we're about to do them backwards. Do you understand? So if you have some rules you don't really understand too well, you better freaking... Now you're very motivated to get those down, because we're about to do them all backwards. The more you know them, the easier this shit's gonna be. So I want you guys to work on number 2. You guys see number 2? All right, go ahead and work on number 2 by yourself, and then I'm gonna have you check it with people around you, compare notes. Go for it. Think backwards. You think, what would the function have been that that would have gotten me this derivative. All right, guys, let's take a look. And by the way, this is the moment when we start shifting gears. And if you learn how to drive stick after you learn how to drive on a Mac, you have personally made this sound. Didn't mean to, I'm sure. I'm sure you didn't do it on purpose. But this is where we shift gears, and that's going to happen. I'm going to see the smoke coming out of people's ears. Have I personally done the derivative when I meant to do the hell shit? Are you kidding me? This is trippy because this is backwards, right? That is the main reason algebra hits people like a brick wall, because all of algebra is backwards. I don't know how much money I put in the bank, but I know I made it. Who are you? Okay, we gotta figure this out backwards now. Trippy shit. So, I didn't really get around to everybody, but most everybody I saw got this one right.
Woohoo!
What's the answer?
X to the fifth.
X to the fifth. There's a little, all of the answers we're gonna have one thing that's kind of wrong, but not really. We'll get there. Just in case you've seen any calculus before, we will talk about it. Yeah, we will get there. I'm not gonna worry about that quite yet. This is n f of x that would have this as a derivative. That is a function that would have the derivative, you agree? Okay. Why do you say that was easy?
Because you just pop the one.
Power rule is a relatively easy rule.
It's very simple, so.
And the 5 just goes back up. So let me ask you this. Let me make one modification that will help us out with something coming up. What if the problem would have been this instead? F prime is 10 x to the 4th.
Well, now you have a factor.
So it will be 2x fifth.
Yeah, if I put x to the 5th, I know I'm wrong. Why do I know I'm wrong? Well, why do I know this has to be part of the answer?
Because it doesn't equal 5.
Why do I know this has to be part of the answer?
Because you're
That's the
going
only
up.
way to get to x to the 4th is for that to come down and leave a 4 up top. Is everybody with me? This is the part where students feel like they're cheating or something silly. No, we're trying to flip and work this shit backwards. We're gonna write down what I know must be there. Its derivative would have a 5 come down. What must have been here already to make it end up with a 10? Do you guys see that? Do you guys understand that that is part of the process sometimes? Is to think exactly like that. What must have been there? Oh, a 2, that's the answer. So if I would have put 10x to the 4th, one antiderivative would have been 2x to the 5th. How do you check yourself?
Work it back.
Before you, yeah, you work it back. You just take the derivative, and that's really easy compared to doing it backwards. You guys with me? You can always check yourself really easily. Especially give yourself a break if you've never done derivatives backwards before. Okay. Part B. A and B are both, I agree, A, B, and C.
Pretty
C's got one little twist to it, but A and B especially are easy because they are directly derivatives of something. There's nothing to adjust. There's no things to add. Where did this come from?
X minus 3.
Now, to be really honest, the real answer should be, and I'm still not fully honest, but the real answer should be this. You guys remember that?
Because it has to be.
You guys remember that?
Yeah.
Okay. So this is what you should be putting down. And even this is missing something that we're going to talk about in a minute. I just want to get this idea down and I'll show you what else is missing. Part C.
1 minus cosine.
We know the answer has to be related to cosine, right? Because what's the derivative of cosine?
Sine.
Negative sign. And the answer to what the real answer is right there. Do I have a negative?
Yes.
No.
Do I have a negative?
Oh no.
No. It must have died somewhere, yes? Or it must have canceled somewhere, whatever gets it through. I like to kill a lot of things when I do this, right? I'm the mathematical Dexter. Gotta get it out somewhere. So, when you start doing these simple antiderivatives, you can write down what you know must be true. I know cosine x has got to be part of the answer. and then you adjust that. Either it needs a number like the 10 needed the 2, right, just a minute ago, or in this case it needs a negative, so it kills it. So this can't be the answer because its derivative is negative sign. So if I just put a negative sign,
You're missing.
then it won't become negative sign. Sorry. I'm a poet and didn't realize. You guys, what's up? Sorry, what happened?
Sorry, I just assumed that since like the derivative of cosine is negative sign.
Yes.
The derivative of negative cosine is just positive sign.
Totally.
Okay, so we're on the same, okay.
Yeah, you're good.
Okay,
How many
thanks for
ways
asking.
is there
Yeah.
to get to this solution? Many. Right, so you're good, Ezekiel. I love it. That's how I would look at it. But I want to make sure everybody's with it. You guys see that? So sometimes antiderivatives have 2 steps. There's a part you know must be there, and then you just do the specific number that makes things work. The only thing that you need to fiddle with, the only thing you're allowed to fiddle with is the constant. The functional part has to be there. So part D. Part D should be even more straightforward than C. What do I take the derivative of to get secant x tangent x? Secant. And what else is there? And what do constants do when you take derivatives? Come for the ride. So if you go down the river, they're there, and if you go back, they're still there. They just come for the ride either way. So what's the answer? Yes. The derivative of that is that. So if I just throw a 2 on, I'll get a 2. How you guys feeling? Do you guys see what I mean? If there are rules you do not know, you're going to suck at this. Even if you know all the rules, you're going to occasionally suck at this because this is weird. Yes? That's the first step to being really good at something, is sucking at it.
So on C, you don't have to have 1 minus cosine x, it could just be negative cosine x.
Oh, I see. We're going to get there. You could have had 1 minus cosine x. That would have worked beautiful.
Okay.
You don't have to. So everybody with me so far? Roughly. You all starting to get the thought process you have to go through. So sometimes you're going to have extra numbers. You're going to have, it's not going to be negative and it was supposed to be negative. So then you can just adjust it. We are totally allowed to do that. We are doing what it takes to figure out what the function was. So of course I'm allowed to adjust it if my first guess is wrong. People don't seem to accept that that's part of the process. You guys get that. It is part of the process. So, for example, if I see an x cubed, what would that have come from? X to the 4th. Yes? You guys with me? Just ignoring the numbers for a minute. If I see an x squared, it must have come from an x cubed. Yes? I know those. The only thing I have to mess with are the numbers. And again, that's the only thing I'm allowed to mess with. Now, is this one okay? This one's a lot like the example I gave up here. That first part here, if this is x to the 4th, what number must have been here so when it comes down it makes 8?
2.
Now, did everybody follow what I just said? It sounded like a sentence you have to diagram in frickin' 10th grade. So I'm sorry about that. It was a bit of a mess. If this is x to the 4th, what number must have been here so that when the 4 comes down, it becomes 8? There must have been a 2. So you put a 2. This one's a little bit trickier, but what do I know? I'm going to leave some room for something.
X to the
I know it had to come from x cubed. There's no other way it could have been an x squared at the end, yes? When the 3 comes down, what do I actually want to have happen?
Right.
I want it to die.
1/3.
Look at, oh, look, he's cute, but I don't care. I want him to die. Kill him. So what must have been here?
1/3.
1/3. Do you guys see that? So very cool with if seeing x squared, it had to come from x cubed. That's where freaking x squares come from when you take derivatives. And then you just think about what number had to be there. The sign is the same, thankfully, so it didn't have to be something. But the 3's got to die. So there must have been a 1/3. Now, if you do this, 8x cubed, die minus x squared. You can check it. Here, before we move on, I'm going to introduce this. If I put a plus 2 here, is that derivative still that? If I put a plus 17 here, is the derivative still that? If I put a minus e to the pi here, is that derivative still that?
Yes,
So what could I put here?
just the constant.
Any freaking number I want to, any constant. So math people, being the creative geniuses we are, we're like, well, we use letter C for constant. And we did that. So if I just put plus any number, I'm still right. Do you guys see that? So what do I have to do for everyone? We already did.
Plus C.
So cover my ass, and if you don't, you're going to lose points. And this is the favorite part of calculus. And this is why, when I was a student, when I got one of these tests, I put a big ass plus C on the top of the damn thing so it would stare me in the face. But do you understand why I need it? I want the most general answer. So, like, for example, x to the 5th plus 7, that derivative is 5x to the 4th. That is an acceptable answer. Is that the only acceptable answer? No, I could add any stupid number I want to, because the derivative of any number is 0. So to represent the fact that I could put anything, we just put plus c. What could c be? Anything. Hell, it could even be complex. But we won't go there. Don't worry. You guys kind of with me? All right. Does that make sense?
So basically, should we just add plus c?
Yes, every time you take an antiderivative, there should be a plus c. I didn't want to throw too many ideas at you at once, though, so that's why I was holding off on that until we kind of got the idea of just how to get the first part. Because now this is just to throw it on there. Now, some of you guys are going to do the plus c too often, and some of you guys are going to do the plus c not enough, and that's just a rite of passage, right? But do you understand why it goes there?
Because it could be there.
Because it could be there. We got to cover our ass. C stands for cover your ass, right? It could have been 11. I don't know. If I gave you more information, could you figure out what it was? So, for example, if I said f of 1 is 2 for this problem, if I said, oh yeah, by the way, f of 1 is 2, could you figure out what c is? Oh, hell yeah, right? You plug a 1 in, you set this equal to 2, and you solve for c. You guys see that?
Yes.
So if somebody just came and told me more information, so what does this have to do with real life? If I told you, hey, graph the line that has a slope of 3, please. I want you to make x, y, coordinate system, and I want you to graph a line with a slope of 3. How many answers could I get? Infinite number, because when I know the derivative, there are an infinite number of functions that have that slope, yes? I'm sorry, I'm yelling at you, but oh well. If I have a slope of 3, that's also a slope of 3. That's also a slope of 3. Run up to the roof, that's also a slope of 3, yes? Go to the basement, also a slope of 3. You guys got it with me? I need you to. So this makes immediate visual sense for the plus c. That just represents the fact that all of those have the same slope, the same f prime. They just have different y-intercepts. And isn't this the y-intercept? Isn't that the y-intercept? Okay. All right, let me stop for a minute. So I understand if we sometimes forget it. What I normally do is I don't take points off unless you do it several times. So from maybe every 4 you lose a point or something. You guys kind of with me? Because it's not really the most immediate important thing, but it is important. We have to know that this should be here. Okay. Oh. So what about this guy?
3x plus.
If that was a 4x, the answer would just be that, right? But it's a 12x, so it must have been this with what in front of it?
3x.
A 3.
Yes.
Thank you. All right. Make him stop, please.
Plus C.
Yeah. Now listen, real quick. Part F would be impossible to do for us right now if I had not done part B of number 1, yes? Can you possibly be able to do something like this thrown at you out of nowhere? No. You would have to know the derivative that led there. You with me? This involves a process we're going to learn in 5.5. Because what's this look? What did it come from? What rule did this use if I take the derivative? Chain rule. Chain rule is really difficult to randomly undo. Isn't chain rule sometimes difficult to just do forward?
Yeah.
And now we're trying to do it backwards, yes? I felt comfortable doing this one because I specifically gave you the function that we took the derivative that led me to this, yes? Since I knew that, the antiderivative is easy. That's why the antiderivative of cosine x is easy. What's the antiderivative of cosine x? What's the antiderivative of cosine x?
It's like
Sine x.
plus
C. Okay. Why is that easy? Because I know the derivative of sine is cosine, so the antiderivative of cosine is sine x. This one not easy. I don't know all these derivatives. Are you kidding me? So, secant squared. What must be part of the answer?
3. Oh.
Tangent. Why do I know this is not the answer? Because what's this guy's derivative?
3 needs to be in the front. Oh.
Secant squared 3x times 3. And is there a 3 out front?
No.
So what must this be over? 3. Yes! Kill the 3. There would be a 3 that would come out because of chain rule, and it's not there. So there must have been an over 3 little ambush I set up. The 3 comes down, yay, look at the eyes dead. Yes? Sorry. You don't like violent
Does the
calculus.
3x have to be in the parentheses, or can it be in front of the 10?
Hell no, it's inside the function.
Okay.
Yeah, 3x is inside the function. It can't go anywhere else. Let me stop for a minute. Yes, sir.
Would we have written f as 6x squared plus 3?
For G?
For f.
Oh, for F. Oh, God. Oh, phew.
So instead of putting the 3 on the outside, we could just put a 6.
No, because this is squared. I only have 1 3, but I have 2 of these. So I can't bring this in. Because then all of a sudden I have 2 3s. I'm not sure what you're asking. I think that's what you're asking.
So writing it as 6x squared plus 3 all squared.
Why would there be a 6?
I was thinking of the problem of B, and
Real quick. If there's a 6 here, and you take the derivative, doesn't the 2 come down making it a 12? But then don't you multiply by 2x making it a 24x?
yeah.
There you go. So again, part F. All right, let me see if I need you guys to. Part F, if I just gave you part F out of nowhere, you would have been completely justified to come up and slap me in the face. Right? Ezekiel got really excited. He's like, excuse me, wait. I have a legal way to slap you in the face? I missed it? What? No. I didn't give it to you out of nowhere, so you couldn't. Nah. No matter how much you want to. Since I gave you F, but I also gave you 1B, I need you to, so I could give you the ugliest function in the universe. We could do its derivative. Do we know the antiderivative of that answer we got? Yes, it's just what I started with. Are you with me? But if I just gave you the function, let me see if I can get you with me.
Well, on that one, so I put the x to the 3rd in the middle, and then I knew that I had to go x to the 4th
Where are we at?
on F.
F?
So if you FOIL that x,
Oh, sure, yeah.
you know you have x to the 3rd, so then you know you have to go up one more.
So
to
if
x
you would have
to the 4th.
distributed, then you could have done it
Then
in a
I
different
divided
way.
the 12 by the
Totally.
4,
Totally.
and then yeah.
Yep, that's valid. I love it. But nobody suggested that, so I didn't. But if you distribute, then you can do each piece the same way this one happened. Yes? Okay. So that one, yeah.
And then you could see
What if
that
I
it has
gave you this though?
squared.
What if I gave you this function here? What you got, Jeff? Okay. And you take this guy's derivative, it would be a product rule with a chain rule on top of that. Jeff, you're thinking ahead. Alright, don't worry too much about the specifics here. Then I multiply those together. If I gave you this function by itself and it said, what is the antiderivative of this? I need you to really get what I'm saying here. If I just gave you this out of nowhere and said, what is this guy's antiderivative? Screw me. Screw me. Screw me. Just forget about me. Just no. If I just gave you this out of nowhere and said, what's this guy's antiderivative? No. 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 You're not going to do it. No. No. You're not going to get it. And understandably, there's no way in hell I could just know where that came from. Yes? But since I took the derivative, what is the antiderivative? Because of the work I did, what is this guy's antiderivative?
3x tan.
This one. Right? And I could put a plus c, but I know it didn't have anything in there, so I could just say that's the antiderivative because that's where the hell it came from. I don't know if you guys are really with me. There are functions that I know where they came from. I know where cosine x came from. So its antiderivative is easy as shit. Even if I put a 4x inside, I could put it over 4 as an answer. Kill the 4 that way. There are a lot of antiderivative rules in our future to handle shit like that. And you guys are like, I don't need to know it, John. Yeah, you will too. You're gonna find out. We're gonna do one antiderivative kind of rule, and then the rest of them are in Calc 2. They live in the first chapter you do in Calc 2. So let's do this. Since I only had a few on here, let's look at a few more. Oh, do you want to take a break? Why don't we take a break? Come back. Here, I'll give you 15 minutes. Come back at 2:15.
Can I see that proof for that last problem? Or
What's
how
up?
How you proved the.
And you guys are all like, that tracks.
More antiderivatives.
Oh, let me introduce this. Okay. So say I have this function. Do you see how it doesn't say f prime? So if I'm given an f function and I take a derivative, we call that f prime. If I'm given an f function and I find an antiderivative, we call that f antiprime. No, we call that, believe it or not, big ass f. Or at least I call it big ass f. Most of my colleagues probably don't call it big ass f, but they miss out on that shit.
Big F.
We're going to develop a rule, and I'm going to show you how it meets what you know inverses should do. Do you all agree with me that finding an antiderivative is the inverse of finding the derivative? It's the opposite by definition. So, I mean, how would I find this guy's antiderivative?
It's gonna be.
Yeah, I know it's got to be an x to the 8th, but it's a poor little 11, dude, right? Yes?
88.
So I need something here that when I multiply it by 8, it becomes 11. And of course, what else do I need? Yeah. So let's do this. Let's develop a rule for the antiderivative of x to the n. Because do we have a rule for the derivative of x to the n? Yes. So let's think about this. If I'm given, Jeff, power rule for integration. It's kind of like the inverse power rule. So remind me, what does big ass f mean?
N plus 1.
Antiderivative, yes. It is the function whose derivative would be little f. Okay, maybe. because to remind you guys, if I'm given a first derivative, can't I find a second derivative? So every derivative is a function in its own right. I could just call it f and then do shit to it. So if I'm given a function, I should be able to find its antiderivative, even if I'm not saying it's the derivative of something. There must be an antiderivative. Stay with me. So where must this have come from? What must the power have been before I took a derivative? You could do this.
S plus one.
Then-
Yes, one more than what it is currently, yes? Because how do I take a derivative? I make the power go down by 1. So how do I take an antiderivative? I make the power go up by 1. Oppa! Okay. How do I know this is not the answer then? Not just because of plus c, but how do I know this can't be the answer? Because what's the derivative of this?
Because
What would this do?
then we
Can we come down? Is it there?
no.
I need you to be with me on what I keep saying. It isn't there, correct? So there must have been an over n plus 1 to kill this when it comes down. A lot of antiderivatives is, oh, that's not there, something must have killed it, right? So if I take this guy's derivative, it is not equal to this. It's off by a number though, yes? If I am off by a constant, I am right. I just need to adjust my answer to that constant. So if I take this guy's derivative, n plus 1 would come down. There is no n plus 1 there. So to make this match, there must be a divided by n plus 1 that was there in the first place. We did this earlier. What was the antiderivative of x squared? 1/3 x cubed. Power goes up by 1, divide by the new power. Do you see how that's the rule? Power goes up by 1, divide by the new power. How does that act with what we just did? Power goes up by 1, divide by the new power. Hey, shit. Do you guys see that? Did we know the rule when we did this? No. But the rule does help when things get weirder. For example, so you guys roughly with me. Everybody understands what I mean. If I have an x to the 7th, the antiderivative needed to have an x to the 8th. From that fact, we could actually reason this out. Do we want to reason it out when I have fractions in the power and all over the damn place? No. I want something I can kind of do. I want something I can sink my teeth into. I need you to realize what we've been doing so far has been feeling things out. You agree with me? We sort of write down, this looks about right. Ooh, we're missing, let me give it to it. That, I agree, that feels weird. You don't do that very much as a student. Most of the time as a student, I'm like, step 1, step 2. This is more like, I think it's this. I'm wrong, let me put a little something here. It's like the Bob Ross approach. I think a little rock lives here. No Bob Ross? Good. I guess some Bob Ross, okay. I think a little 7 lives here, Jeff. Okay. So what if I had yeah, let's just go straight for the weird shit. Yeah. Yeah, whatever, Jeff. You weirdo. The rule is the exact opposite of the derivative rule. You guys see that? The derivative rule is multiply by the current power and then subtract 1 from the power. Yes? Isn't that what the rule is for the derivative? For the antiderivative, it's make the power go up by 1 instead of down by 1, divide by the new power instead of multiply by the old power. Everything is backwards. Perfectly backwards, which makes perfect sense. It's supposed to be the inverse operation. So what do I need to figure out first when I'm trying to find big ass f? When I'm trying to find the antiderivative. What do I need to figure out? Very first thing.
Plus 1 px more.
Yes, the new power. This would be x to the.
5
Now here's what's beautiful. Yeah, here's what's beautiful. Remember derivatives? We subtracted top minus bottom, put it back over the bottom. Now to do antiderivative, I want to add 1. I add the top to the bottom and put the answer back over the bottom. Because it's the inverse operation. What's negative 4 plus 9?
5 9.
5.
5 and put it back over 9, yeah. Let me see if you guys are cool with the next bit. Therefore, I must be dividing by what? 5/9. I have to divide by the new power. That's what the rule says, yes? Add 1 to figure out what the new power is. Divide by that. But what is dividing by a fraction? Multiplying by its
reciprocal.
yeah. So I'm going to put in front of 11/13. So I'm going to put 9/5. And then this I've chosen poorly. What is that, Jeff? Good job, buddy. I think.
99/65.
Thank you, Joanne. Okay. Gross. Gross looking. Easy to do. That's my hope. So you would expect, even though antiderivatives are always more difficult than the associated derivative, this rule should have been the easiest rule, because power rule was the easiest derivative rule, yes? So undoing that should be kind of like the easiest integral rule. Maybe, I'm sorry, I said a word there. The easiest antiderivative rule. So you get all the same shit. All the same shit as before. What do I mean by that? I mean, if I give you this here, and I say find the antiderivative, so I really want to lay this groundwork with you. Even if I was taking a derivative, I wouldn't do this, but quotient rule exists for derivatives, yes? Do you understand it cannot exist for antiderivatives? Antiderivatives are trying to undo the shit that was done. I am not going to have something as straightforward as quotient rule to undo quotient rule or something. You guys follow it all? What do you think I should do here besides push the paper up and forget I wrote it? What did I keep saying? What was one of the main things I kept saying? You're about to do calculus to a function, yes? If you're about to do calculus to a function, what do you do to the function first? Simplify!
Yeah.
Simplify. How do you simplify this thing? What am I divided by x to the 7th?
4x squared.
Everything. So this would be 4x to the negative
5.
5 minus 3x to the negative
6.
plus 2x to the negative
7.
yeah, right? I'm divided by x to the 7th, so I basically just subtract 7 from all the powers, because that's what you do. When you divide like bases, you subtract the powers. You need to do big ass F now. Big ass F. Here's where people get tripped up, though. Same place y'all got tripped up with derivatives. Negative powers always trip us up. I want this power to do what? When I take the antiderivative, I want this power to
Plus 1.
go up. So that becomes x to the
-4.
negative 4. Now what's really nice is, I don't know if you guys, well here, let me write all this down. So what's it divided by?
-4.
Did some of you guys see there was a shortcut there? Because I had exactly
Bring that forward.
what I needed, yes? But it's okay, you can just apply the rule, who cares? Is everybody with me? That's the rule, yes? Find a new power, divide by it, yes? That is the power rule for antiderivatives. Then I'm going to have minus,
3x to the negative 5.
yeah, x to the negative, Jeff, you just did the thing. X to the negative 5th divided by negative 5. And that can simplify that. Plus 2x to the negative 6 divided by negative 6 plus c. And now I can simplify stuff, yes? Are you guys with me so far? We applied this rule before we knew it existed. Do you all understand what I just said? We applied this rule. You applied this rule before you knew it existed. Now we know the rule exists. We can use it for weirder situations, especially fractional situations. They get tricky as shit.
Definitely you kind of like.
Yes, trying to figure out what would have been there. Oh my god.
The quotient, you have to use the quotient formula, and that would be,
Well,
I mean, not impossible, but definitely more trouble than it.
Yeah, we don't have quotient rule for antiderivatives, but yeah. So this one, if I simplify it, okay. So one way to look at this is if we learn an idea in mathematics, to really understand it, you have to be able to do it backwards. That's more than what this is more than that. This is, we're gonna figure out what the physical meaning is behind this. What's the physical meaning behind taking the derivative? Slope. And more generally, more like physically applicable is rate of change, right? So if I take the derivative of the wind speed function, I'm figuring out the rate of change of the wind speed. So as a hurricane comes in, I'm like, oh shit, my derivative is going crazy. So, you gotta watch out. You guys kind of, there is a physical interpretation to antiderivatives. We don't know it yet. That's gonna be the next bit. The next bit of our journey is gonna be figuring out what the physical interpretation of this is. Okay. Trying to remember. Yeah. Let me ask you one more. You ready? Does anyone remember this? No? Alright, this is perfect. This is perfect. Paolo, you just did an amazing thing you don't even know. There's no way in, and please don't take me. I'm ready. You're perfect. Nothing wrong with your guess. But I'm about to say something that sounds wrong. There's no way in hell this is ln of 1 plus x squared. Why not?
Because there's
Chain rule would tell you what would need to be up top. If it was ln of 1 plus x squared, wouldn't that be 1 over 1 plus x squared times 2x? Is there a 2x up top? Are we missing more than just a constant then? Are we missing? What are we missing in order for this to be a direct antiderivative? We're missing,
X or variable.
in order for this to be a natural log, we're missing 2x. We're missing a functional piece. We're missing more than just a number. Do you guys see that? Do you guys see that? So here, let me make sure you guys really understand. If we thought this could be related to this, and let me just do this. If we thought it could be related to this, well, what is this guy's derivative?
2.
2x, 1.
Yes, it would be 1 over 1 plus x squared times 2x, yes?
Can you just add the 2x to the denominator?
Here's the problem. It's only a constant I could be missing. I can't give little f dude what he's missing if it's more than just a constant. I need this to make sense. I can't,
So it's missing a variable.
there's no way this could have come from natural log of 1 plus x squared, because in order to do that, it would have to have x over 1 plus x squared.
Can you put it to the negative on the whole thing and then just do the chain rule? Like rewrite it as a negative one?
Antiderivatives do not have chain rule. Do derivatives have chain rule?
Yes.
Antiderivatives would have to have an answer to chain rule, a way to undo it. So do we have chain rule for antiderivatives? No. We do have a process to undo chain rules. Yes, we do have that. But it's not going to be as straightforward as chain rule. I need you, if we're doing everything opposite, if antiderivatives are everything opposite from derivatives, I need you to be with me on this. Everything's going to be a little worse. Everything's going to be a little worse. Because not only do I have to think backwards, I also have to undo things that were done. And those things could have been weird themselves. Yes, like chain rule is pretty weird. Product rule is not that weird, but it's actually pretty weird. This is perfect. I didn't even mean it like this, but this is perfect. If I am missing, do you all agree I'm missing an x here?
Yeah.
So really quickly, if I would have put, we'll do this, if the problem would have been this, then what am I missing?
2.
I'm just missing a 2. So then this would have been natural log of 1 plus x squared divided by 2 plus c. If what I'm missing is an x, I'm not missing an x. I just don't have that function. I need this to make sense. It's not a question of, oh, I'm missing it, let me give it to it. No, I don't have that function. So it can't be that.
Yeah, you gotta modify the function until you have something close to a correct answer, but you gotta mess with it a bit before it actually makes sense.
But I'm only allowed to do that with constants. Okay. Does anyone remember the derivative of the inverse tangent? So what is the antiderivative of 1 over 1 plus x squared? Completely different from natural log, yes? Because it's a completely different function. So, real quick, when you're taking derivatives, if I have two functions multiplied, can I just take the derivative of each piece and multiply those together? Am I allowed to do that? If I have, like, for example, if I'm trying to take the derivative of this, is the answer just 2x cosine x? Is that the answer? No, right? I have to use what? Product. So if I have the product of two functions and I'm trying to find the antiderivative, can I just take the antiderivative of each piece and multiply them together? I need this to make sense. If I can't even do it when I'm taking a nice derivative, ain't no flipping way in hell I could do it if I'm taking the antiderivative. I need you to understand this. If I got more shit going on with a derivative, things are worse. You agree? If I have more shit going on, meaning stuff is multiplying and so forth, it's going to be way worse for an antiderivative. I'm not trying to make you feel like, oh shit, what are we about to get into? I need you to realize that so you don't make simple mistakes. So this guy's derivative is not this. Is everybody cool with that? What did I do wrong? Yes, each get a turn, right? So the antiderivative, sure as all flippin' hell, is not this. I can't just take the antiderivative of each piece and multiply them. I wasn't even allowed to do that when I was going forward with derivatives. How the shit would I expect to be able to do that when I'm going backwards with antiderivatives? Do you guys see that? That's one of the easiest mistakes people make when you're learning antiderivatives, is you start to do that. Well, you can't even do that if it was a normal, nice, easy, forward derivative. Ain't no way in shit you could do that backwards with these antiderivatives. So how do you do that? You won't learn that till Calc 2. That is an antiderivative you cannot do until Calc 2. Do you understand? So it's beyond us at the moment. If you're going to say Calc 2, you'll know it. If you never take Calc 2, you'll never know it. Too bad. Or you can study yourself. Okay, maybe. So at the moment, we can only do antiderivatives of things that we know are direct derivatives of something else. Minus like constants. Constants, we can make those work. Okay, maybe you guys are with me. What I'm trying to say is we don't know much of anything yet. And of course it makes sense. We only just started talking about these things. Now, what's really trippy, what if I had this instead? Gotta figure out big ass F here. Of course I can, right? What would big ass F be?
X to the third.
Let's put a cosine. Yeah, it would have to be good. You guys see that? Cosine would be negative sign. This is positive sign, so it must have been minus cosine. Let's see. Okay. And that makes more sense because derivatives I can do separately if it's plus or minus. Yeah? Okay, maybe. Okay. So here's what's gonna be a little bit weird. We are going to take what is going to appear to be at first a major turn in topic discussion. We're going to get into chapter 5 just a bit. I'm going to introduce a symbol that we're going to use in chapter 5 a lot and make sure everybody knows how it works. Because it's going to show up everywhere. And I want to make sure you guys know it. The first thing we're going to talk about, seemingly completely unrelated to antiderivatives, is finding the area under a curve. So for example, just to give you, I want to do two things in 10 minutes. I want to do the motivation behind what we're about to do, and then talk about this symbol I referenced earlier. Okay. So, real quick, if my function was a constant, and I want to know the area. Is everybody with me so far? The function is 7. So what's the graph look like between 1 and 6? 7. Yes. And I want to know what's the area between the x-axis and the function. Can you find that easily? I want to know the area between the x-axis, the ground, and the function. Like this is a ceiling. Yeah, with just how wide is it? 5. And how tall is it? So what's the area? Beautiful. Is everybody with me? No, too bad for you. It ain't going to be like that. Some problems are going to be this. They're going to be triangles and shit. You just have to remember your geometrical formulas. If you forgot, look at the back and the front of the book. Because I forget where it is. So this area is easy. Now, can you do the same thing if I have Jeff, make that big. X squared from 1 to 2, and I want to know the area. You guys remember your top side curved down formula from geometry? No, there is no such thing. I appreciate somebody looked at me like this. I'm like, that is the correct answer. The correct answer is, what the hell are you talking about, John? We ain't got no such thing. Is there a simple geometric formula that you can use to figure out that area? Huh? Is it a rectangle? I want to know the exact area. Do you understand? I want to know the exact area between the parabola, y equals x squared, and the x-axis from 1 to 2. Do you understand my question? Yeah, hold on to that. Don't bring it up yet. Sorry, Bob. Yes. You guys, I need you to be with me. Do you understand the first problem is easy as shit? If I made it a slanted line, then it would have just been a trapezoid. Ooh. But the minute I let one of them be curved, and not like a circle, but this is not a circle, this is a freaking parabola. I don't have a souffle deflated function for area. Yes? Yes, with me? I don't have an X-Acto knife edge, is what that looks like, sort of. No, sort of. Maybe, not really. So, what we're about to do is to develop a method to get the area between a function and the x-axis, right? We're going to do that before we figure out why we want it. Because that's how math sometimes works.
It's a skateboard ramp.
One symbol we're going to use along the way is this symbol. Let me write it better. There we go. This is the symbol after a good weekend. Go lay down. There he is. Does anybody know what letter this is?
Sigma.
Sigma. This is uppercase sigma. In case you took statistics and you've seen this dude, this is lowercase sigma. Get out of here. We don't need you. Uppercase sigma. So it's the Greek letter S, effectively. Anyone ever use this mathematically? What way? It's the sum. See, math people, remember they're very creative. We're like, well, let's use something. Let's use Greek letter S to mean something. Because we're very creative. We want to use a Greek letter to make it look all official. So here's how this works. This literally means the sum of. So it needs stuff inside of it. It's like the square root of, the natural log of, it's the sum of. So without shit inside of it, it's just the Greek letter. If I do this, I'm still missing one thing. It says to add up, and I'm using the drunk E, but it's too bad for everybody. Get out of there, Jeff. This says add up I, but I haven't given you enough information. What's a really good question?
What's the rest of the information?
Okay, good. A really good question though is what the shit is I?
It's
I'm
magic.
like take psychology class. No.
If.
I is the variable we use primarily for these things, these sums.
If.
Lord, that's loud. I have to tell you what I starts at and where I goes to. So for example, I starts at 1 and goes to 4. So summation symbols, unless otherwise specified, and the specification would be really specific and the class would not be this one. So I'll just say it this way. Every summation symbol for us, it's going to increment by 1. So what is I at first? 1. What is I next? 2. So this sums up all the values of I for I from 1 to 4. So this would be 1 plus 2 plus 3 plus 4, which is
5. Oh,
10.
10.
1 plus 2 plus 3 plus 4 is 10. Is that okay? So what about this? How would you do that? Yeah, what is I at first? 2. 2 squared minus 5 is -1. Plus, what is I now? 3 squared minus 5 is 4. I is 4, yes, 2, 3, 4, 5, 6, 7. When I is 4, I get 16 minus 5, 11. Are you guys understanding what's happening? So it's a combination of function inputs, right? Inputting for I, and then just adding those together, because the big symbol means sum. The yellow one's a sum. The big E means sum. And I would just keep going till I equals 7. Dear God, Jeff. I equals 5 would be 20. I equals 6 would be 31. I equals 7 would be 44, and then whatever the shit that all adds up to be. You guys with me? So there's 2 steps here, and both steps are easy as shit. One of them is add these things up, and the other one is plug these things in. Okay, maybe. So last thing. What was the last thing, Jeff? I don't know, I had something. Oh, what's the difference between what we just did and this? This says, what's that? Take away 5. So you would do 4 plus 9 plus 16, blah, 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 blah. And then at the end, you would take away 5. You guys see the difference? Because I didn't specify all of this was inside the sum. Therefore, that's that thing. Take away 5. Are you guys at all with me? So it follows all the same order operations rules as before. Okay, maybe. Okay. Does that make sense? Especially to my people who've never seen that symbol before. Does that make sense? You can plug numbers in. You can't, I don't know how you make it, but if you can plug numbers in, you get numbers. And then you add those numbers up. That's how you evaluate summations. So this is officially called a summation symbol. This is summation notation. The sum I equals 1 to n, or let's say a to n, f of I. Because I'm trying to be a, because the initial thing can be anything. Most often the initial one's going to be 1. Sometimes it could be 0, and then sometimes it could be anything. But most of the time it's going to start with 1, if I remember this book correctly. So that's gonna factor into the first 3 sections of chapter 5. Just to like one little seed for next time. If I wanted to estimate the area of that circle, I could use little blocks that are 1 by 1, and I could put them in the circle, and I could just count how many there are, and that would be an estimate. Do you guys agree? You guys agree? Yes? So we're gonna build a process where I take the area of the function. It's gonna be a shape. Yes? It's gonna be some funky shape, and I'm gonna slice it up into basically little rectangles, and then add them all up, and that's where the summation symbol is going to come in, right? And then we can estimate the area, and then we'll talk about how to make that become a perfect area. So we'll do that next time. That's enough for you. Okay.
Thank you, everybody.
Oh yeah, I did have a. We'll do this next time. Darn.